two more circles into here. Okay, so one is here, one edge is here, one edge is here. So we're going to draw two more circles. Okay, so the two circles over here I'm going to draw. Right, so 1.5. So this is one circle. Right. Before I draw the two more circles, I want you to observe this. Okay, I want you to observe this. So I'm going to draw. Come on, Eugene. Okay, I want you to observe this. I draw them in green, right? So this is our tau max, right? When we drew our 2D mole circle, yes or no? It's our tau max, okay? Right? Okay, so imagine you don't have that small circle in there. Okay, in 2D mole circle, that is your tau max. Now, when we incorporate 3D mole circle, okay, so 2, 4, 5, 2.5. So I'm going to incorporate 3D mole circle now. Okay, so now this is 3D mole circle. Okay, so you will ask me, Eugene, there is a lot of circles now. Are we still at McMaster or are we in a circles? Okay. Okay, sorry, a very lame joke. Okay, so the outermost circle is the circle for the XZ plane. Okay, now don't worry about this. Okay, I'm just giving you a flavor on 3D mole circle. Okay, this one is for your YZ plane. Okay, and this one over here, right, the one that you see over here, that is for your XY plane. Okay, do not worry about how to label the plane yet, especially these two. This one is known because we drew with what? With XZ point. That's why it's what? XZ plane. Okay, now, question for any of you. Is there any difference with our tau max using 2D mole circle and 3D mole circle? Is there any difference? Anyone?
There's two more circles?
No, but is there any difference with the tau max? You cheeky sort. Vidu-san, I know there's two more circles.
No. Does it depend on the plane?
No, the tau max, right? When we draw 2D mole circle, did not change at all, did it? Right? That is for this reason. That is why when using shaft design, we only need to do what? We only need to use 2D mole circle. So this proof, yeah, this shows that for transmission shaft design, okay, 2D mole circle is sufficient.
And Professor, would another way of thinking about that be like, because we're only concerned with the forces in the XZ plane on the element, since it's only X and Z, can you consider it a 2D Moore circle? Like if you had to worry about the force like in the Y component, then because our strain Y was equal to our stress Y was equal to 0, so therefore there was no Y to our element.
For that's why this is so unique for transmission shaft. Okay, it will not be so unique if the shaft, now if our shaft, what you see is, I'm not saying it's wrong, okay, when your shaft inside, when it's hollow and you force water or water or fluid, high pressure fluid into the shaft, because it's going to generate a what? a y.
Force in the y direction.
Yes. So for our case, it's unique. Okay. That's why I say what this is very unique for what transmission shaft only. Okay. But however you want to design a transmission shaft with fluid flowing in, it is a different ball game. Okay. I don't know why we would do that for our transmission shaft. Okay, but be aware. Okay, so this case it will not be applicable for shaft that is having a fluid in there. Are we clear? Okay.
Okay, so like would the general rule be as long as you can draw your element in 2D space and there's only
No. You can't say that because we
No?
can draw this in 3D. Okay, we can draw this in 3D now, right?
But
We
there
can
wouldn't
draw
be
this-
any force in the y.
Yeah, but we can have force in the y also, and then we can have force in the x. Okay, so okay, Connor, don't generalize anything at this stage. Okay, until we have the experience. I know you're thinking ahead,
Okay.
which is a good thing. Okay, don't generalize yet. I want you to receive this with an open mind. Okay, we are like tree huggers. Okay, receive this with an open mind first. Then later on, when the loading condition change, then we know what's going to change. Okay. Right. Okay. So 2D Mohs circle is sufficient. Okay. This is because with 3D Mohs circle or 3D Mohs circle analysis, okay, tau max did not change. Okay, so this is the thing that I want to drive. Okay, so that's why we can still use what 2D Mohs circle. Okay, so now I'm going to copy this circle. So the next step, what I'm going to do now, okay, what I'm going to do now is, wait, let me draw my axis first. I forgot my axis, sorry. So I'm going to write out a few formulas, and these formulas are Mickey Mouse formula. When I say Mickey Mouse, it is really easy, okay? So again, this is our normal stress. This is our shearing stress element, rotation clockwise, anti-clockwise, okay? So we know that our stress average, okay, we're going to calculate our stress average, okay? So stress average, or rather than saying stress average, I want you to get used to the term. So this is the center of circle. Okay, so this is our stress average. So in this figure, the stress average, okay, so this is our center line. So the distance from here to here, this is our stress average. Okay, so the stress average, as you can see over here, is equal to normal stress X plus by normal stress Z divided by 2. Okay, so we know that this is equal to 0, right? Stress X is Z is equal to 0, and then we come out to have stress X over 2. Okay, and I'm just using the notation that the textbook used, and we're going to let this equal to stress M divided by 2. Okay, so this, and I'm going to define what is stress M. Okay, so where stress M, right, where stress M is the stresses induced by the moment when the shaft is not under axial loading. So when there's no axial loading, okay, the term that is used is stress M. And that is true in most of the case. So when I wrote this out, okay, okay, this is more of a general solution. Okay, so this term over here is more general. General means what? I assume there's a normal stress loading on the shaft. Okay, but if you look at a shaft like this or a system like this, right? It is just what you have a motor over here. You have all your gears. Okay, what you see over here, you don't have. This is a normal transmission shaft. Why I say normal? Because you have no what? Stress X is equal to what? 0. Okay, that is the normal case. Okay, so that is why we coined the term. Okay, we coined the term over here, right? We coined the term over here, sigma M, because stress induced by it's the stresses induced by the moment when the shaft is not under what? Axial loading. Okay, so the next thing that we consider, okay, next thing we have to consider is we have to look at how to find tau max. Okay, so tau max is again this tau max over here. So you guys seen the formula yesterday. So tau max for this case, okay, for this case, tau max or radius of the circle okay, tau max is equal to stress average squared plus by shear xz squared. Okay, so where some of you might say, Eugene, what are you referring now? Okay, so I'm going to sketch over here. Okay, so the distance from here to here, right? This is our shear x z, and then this, yep, and then this over here, you can see this is our sorry, I'm colorblind, okay, and as you can see, this is our stress average. So we are taking these two distance and the shear xz, okay, and sorry, not the shear, and this is the radius that we are trying to find. Okay, so this line is the radius like what I've shown you yesterday. Okay, so this is our radius. So the radius of the circle is our tau max. Okay. Okay, so the tau max is a critical component. Okay, the tau max is a critical component. Let me briefly describe about tau max first. Okay. Let me describe. So I'm going to describe the importance of tau max. Okay. So if we look at tau max, okay, we look at tau max. Okay. Or not the importance, how to obtain tau max from uniaxial tensile test. So you can also determine what is a tau max for uniaxial tensile test. Okay, so So this is obtained by, so we are going to carry out unit axial tensile test. So one direction. Okay. So this is P prime. So if we have an element, right?